Hello world, it's Craig. A little more on this C-44 single board computer before I put it away and get back to some of my other projects that I'm working on. Now, after the last video, a viewer dug up some extremely useful information on the C-44 bus. And specifically included in that were a number of cut sheets on some QSI cards. Now, QSI is a company. They are in Utah. And so they may be the company that I kind of had a thought that they existed, but I couldn't remember the name of them that I mentioned in the last video. But we now have the C-44 bus specifications, and in this is, the most useful thing I think is the pinout for all the fingers on the card, and also a little description from them. So rather than relying on, my aging memory of this, we can go right to the fountain of knowledge, and if we have a question on any of these fingers, we can see exactly what it does. And that includes a couple of things, like one of them is how to take a card out of hibernate, because all of the C-44s had this low power hibernate. So we can see how to take it out of hibernate. There's a wake signal, there's interrupts, or you can do a restart according to this document. And let's see, in the last video, I did have the first two pins swapped. I would have probably found that when I owned this out before I applied power to it. And what else was in the specification? Oh, there's also an external reset, which will be handy because I want to put a reset button on this. So it's really great to have this. I really appreciate the viewer that sent this in. And, if we do have any more documentation on this particular card, that would be extremely useful also. Now, as a next step, I just want to get this board started up and hopefully map out the RAM, or at least learn a little more about the board. And I don't want to, start immediately by drawing a schematic and, probing this thing out and trying to figure out where all the traces go. What I'm going to do is I'm going to try to use my little serial port dongle doodad. Now, this video may be a little bit chopped up because I'm going to do this, we're going to record it in real time. And, this is going to be over a few days or a week or however often I get back to this board. So I'll do a few little steps, and this project's going to go on in kind of fits and spurts. Now, I have a whole box of these 22-pin card edge connectors. I'm not sure why I have so many of these, but, I've got a nice collection of these, and I've got some good wire wrap ones. And I don't think it's worth risking damage to the board with, a flaky connector, putting little pins on this or probing or whatever. So it's certainly worth dedicating a connector, to this board for the power and the reset. And then also if I use a wire wrap one here, I have, these little stubs that I can put DuPont connectors on. And I certainly am not going to solder to these fingers. I see where some people solder to these fingers, and it drives me a little bit insane when I see that. So the next thing I'm going to do is I'm going to make a connector dedicated for this that I can just plug this in and not worry about the power and so forth. So let me go ahead and do that, and then I'll be back with the next part of this video. Okay, I made up a little connector here. We've got power and ground. So this is our rough input, which was anywhere from 8 to 18 volts. And I added a little fuse to it, and also over here on the regulated, so remember this board's got this onboard little buck converter. It's taking this rough voltage, regulating it down to 5 volts for this board, as well as all the other boards in the system. And since I don't necessarily trust this buck converter, it hasn't been used in 30 years, so I put a little Zener diode crowbar over here, about 5 1/4 volts or whatever. This'll start to conduct, and this avalanche, and it'll blow the fuse. So that's the idea, is that if anything goes wrong with this board or that buck converter, it'll blow that. This will start to conduct, and it'll blow that fuse. And this is I try to keep things. I've tried to get a little bit more organized, and one of the things that I've done is I've standardized on these little Molex mini fit connectors for my power. So right now I have this connected to bench power supply over here. I can bring it up slowly and adjust the voltage. And then eventually I'll switch over to just a wall wart, a 12-volt wall wart, or a desktop one like this guy here, and I have the same connector on it. And on all of the connectors that I use, or all of the power supplies I use the same format, so that I just make sure that, I've come really close to applying the wrong voltage to a board before. And, it minimizes that chance of that error if I use this and they're standardized. So I've got plus or minus 5, minus 9, plus or minus 12, 24, 48. So all my standard voltages that I use are always in the same place in this connector. Power on this side, and then each of them have an individual return on the back side. So this is one thing that I would recommend that people that do this, where they're working on a bunch of different projects and swapping things out and swapping power supplies out, standardize that connector. That's one of the smartest things I've done in the last few years. Okay, so that should be good. My power supply's off. Going to plug this guy in and slowly bring the power up, over a few hours at least. Maybe give the capacitors a chance to reform a little and get it up to where that converter is actually switching. And I'm going to watch this output here and see how that output goes. All right, now I've brought up the rough voltage. I'm now at a little bit more than about 4.25 on the rough voltage, and our regulated voltage is right at 4. Interesting that as I brought the voltage up, the regulated voltage is approaching what the rough voltage input is. These CMOS just aren't taking that much current. It's not challenging this buck converter at all. So right now I've stopped at 4 volts. That should be enough. Everything should be up and going. The minimum voltage on most of these is 3 volts probably. So everything on this board should be up and going. All we have to do is apply some code for it, give it some code to run. Now my first goal is just to run that little program, establish serial communication, and let us start looking for RAM. We've got 2 RAMs on this that we're looking for. There's this 8K in this little Toshiba, and then there should be 256 bytes in the 8155. So we should have 2 blocks of RAM once we get up and running. Now once I find the RAM, then I can start writing code, that uses a stack pointer, and then continue investigating this board from the inside out, as I mentioned, rather than go through and do all the traces first. Now that sounds great, but of course the first difficulty is this board, at least as far as we know, it doesn't have a serial port. And now with the 8155, presumably, we could bit bang one out of its I/O port, but we have no idea where those ports are, what they're mapped to, what their port addresses are, and we don't even know if they're I/O mapped. They could be memory mapped. So we have no idea how to talk to this 8155 yet. And presumably all of its I/O come off onto this connector, but we don't know where they are. So without doing a bunch of probing on this, I'm just going to use the software. Now, even if we had a serial port, the next big problem is that we can't use any RAM because we don't know where the RAM is. In fact, we don't know where anything is mapped, as I just mentioned. So this is a good task for my little PROM to serial port adapter. This lets me add a serial port to this EPROM socket, and I can replace the EPROM with this ribbon cable. I plug this into this socket, it comes over to this dongle doodad, and then I have my code. So I have got a little ZIF socket here that replaces that EPROM, and I can run code in this. And this is the same as I used earlier on my, I have one over here for the 1702A that's running on my Intellect system. So I have this one that's for 1702s, and then this one is from the 2708s on up to the 27256s. Now fortunately, this board has the silk screen indicating it's 2764 EPROM, so I have a bunch of code, or I have the same code. It's a 1K block of code. It fits in any EPROM from a 2708 up to the 27256. So all I got to do is put in a 2764 EPROM, have to switch to the bigger cable, and we should be good to go with this. Now I'm pretty sure that I'm going to hit some roadblocks here, that it's going to goober up my plans. And I'll tell you more on that in a minute, why I'm just a little bit pessimistic of this actually working. Let me switch this around for this board and we'll come back. The only thing that we know for certain about this board is it's an 8085 CPU. And possibly, maybe surprising, but that's the only thing we need to know about this in order to establish serial communications and start running code on it. We don't need to know where any of the mapping is. And the reason that works is that we know, since this is an 8085, after a reset, it's going to set the program counter to 0 and fetch that first instruction. So when they designed this board, they almost certainly made it so that right after a reset, the base EPROM is mapped to 0. They might change that later, but the base EPROM has to be at 0 so that it can fetch its first instruction. This board only has one EPROM, so we don't even have to guess which one is the base EPROM. It's an educated guess that this is actually configured for the 2764, but we have no idea what EPROM this is set for. I have my suspicion that these are universal sites because it's got all of these jumpers around here. There's a dozen jumpers all over this board, and I suspect that those are to set the configuration for this EPROM, or in part set the configuration for this EPROM. So we'll try it with a 2764. If that doesn't work, then we will try 2732, 2716, and maybe we'll even go up, maybe a 27128. But we'll start with 2764. That makes the most sense. I hope it works because, my boast was that I could start communicating with this board without knowing any of the details on it. I don't even know the clock frequency. Well, I can read the clock frequency, but, I don't know if I would trust that clock or that crystal after all these years. So we're not even going to worry about the clock frequency. As far as the code goes, obviously, since we're looking for the RAM, we can't use any RAM in this code, and that's why I referred to it as RAM-less code. And that means that, there's no stack in this, which means there's no traditional calls because there can't be a return because we didn't have a place to push on the stack the return address. So in this RAM-less code, there's no calls, and we don't have any storage buffers. So only the memory that we're using is what is in that EPROM. We're not using any storage, any buffers. So if a value can't be saved in a register in the 8085, then that value can't be saved. So, in all this code, we're limited to the number of registers there are for all of our stored variables. And it probably isn't an interest, general interest, but perhaps, we'll dig into writing RAM-less code sometime. But if you want, to get a taste of the limitations, you can take it as a challenge to, bit bang out a serial interface without using any RAM. And I think you'll find that it's quite challenging. Now, writing RAM-less code, it can also be annoying, so I don't do it any more than I need to. This is just to get us going to find out where the RAM is on this board, and then we can get back to our regular programming. And you can probably imagine with no RAM and only a 1K limit to fit in the 2708, which is the smallest EPROM that this board can handle, then, it's this little probe software that I have in here, as we'll see in just a second, is fairly limited in features. I'm bit banging the serial. Rather than have to know what the bit values should be, the delay values, the first thing that this software is going to do is it's going to use autobaud to find what the frequency is or what the bit values need to be in order to do the communication. So let me go ahead and bring the power back up on this. Let's do a reset. Let's look at this in Terminal Emulator and see what we've got going. All right, so we are powered up, and the voltage, I had to bring this back up to 4 volts. So I'm applying quite a load on it with this little dongle because, this isn't CMOS. In fact, this isn't even a CMOS EPROM. So now I've got almost a volt drop across this little buck converter. I've got 5.1 volts coming in, and I'm at 4.1 volts on the output. Okay, so let's do it a reset, and let's look over here on my TeraTerm setup serial port. I've got it on COM8, which happens to be that one. I'm going to try 1200 baud to begin with. It doesn't really matter, but that is quick enough that the calculated value should be fairly reasonable. So the first thing I have to do is give it a space. Let me give it a space, and this is fantastic. It comes back and it gives me the sign on. So giving it a space allowed it to calculate the baud rate, and it came back and it said, okay, hello world, and these are our 3 commands. We can either do a dump, we can do a fill, or we can map. So that's very nice, very nice indeed. It figured out the baud rate, and actually it didn't, not just the baud rate, even better, it figured out the necessary bit delay values. So I can come back and I can do another reset. Let me set up, change the serial port. I can change that to, let's see if we can do 2400 baud reliably. Okay, so now we're at 2400 baud, and that seems pretty reliable. So that's great because our dumps will go even faster now at 2400 baud. All right, so we have established communication with this. And, that's a very good thing. And it's quite satisfying to take something that we know nothing about and we're talking to it. So the first major hurdle has been crossed, the board's fired up, the CPU fetched our instructions, and everything's going according to plan. So first of all, we can see that there's only a few commands. We can dump memory, we can fill memory with a specified value, or we can do a search for RAM. And all of these are straightforward. They're going to perform the operation starting at address 0 and go all the way up through memory to FFFF. And the idea is, as I said, that as soon as we can confidently map out a portion of this RAM, or at least enough of it that we could have a stack, we can then go back and start writing real code, and then we can really dig in to start figuring out the I/O ports. We need to know where the I/O ports on this. We need to know the memory mapping and what other hidden gems there are on this, because we know, for example, there's a way to put this in either a halt mode or a hibernate mode. There's ways to get it back out. So there's these other hidden gems that we have to find also. But right now it's all about finding the RAM. We're looking for the 2 blocks, this 8K and the 8155. Okay, so that looks good. And, why do I think a problem is going to show up? As I mentioned, there's other gems in here. We know that this can be put into that low power hibernate mode. Somehow it's got to get into that mode. And to do that, there either needs to be an onboard port to set a hibernate bit or a memory mapped port that would do the same thing. And my program doesn't tickle any ports. So as long as, their tripwire to put this in hibernate mode is a port and not memory, and if it's an I/O mapped port, not a memory mapped port, but if it's a true port, it's port mapped, I/O mapped, then as I go through and I do a dump or as I look for the RAM, I'm not going to trip that tripwire. But if it is memory mapped, then as my program works that memory space, there's the distinct possibility, in fact, if it is memory map, it's going to hit a memory address that puts this board into hibernate. And if that takes a specific bit right, then our chances go up that we can at least do a memory dump or a memory read, and we won't run into trouble until I come back later and I try to do a memory fill, or I try to search for the RAM, which is essentially just going through and putting something into all the memory locations and see if it sticks or not. And if it turns out that it's triggered by just a memory address read, then our chances of even getting this program to run, goes down, because it's going to go up, and as soon as I trip that bit or that memory address that causes this guy to go into hibernate mode, it's going to go up to a certain address and it'll go into hibernate mode, or maybe it'll remap the memory. Who knows, what they could do, because I don't think they would have wanted to run an operating system, CPM or something on this. If they were running CPM, they would have to be able to switch that around so that the RAM then was mapped to 0. And I don't think they would have been running CPM, certainly not in the field, but maybe, if this didn't go to the field, maybe somebody would want to run CPM on this. So I just don't know what tricks they had up their sleeve when they were designing this, how complicated this is going to be, and what tripwires are in this. So anyway, that's just a haunting thought I have in the back of my mind, that my probe could actually just trigger something right off the bat, and it's going to send my program off and search for the promised land. And it's going to look like it crashed, but really what's happening is it just jumps to someplace, and then, if there was a memory swap or something, when it got there, there wasn't any code up there, or maybe it was a hibernate. We're just going to see that this thing goes into hibernate mode. Anyway, so let's just see. Let's just go off with high hopes and optimism. Worst case, I have to go back to the basics, track down the chip selects, and work backwards to figure out the memory map. And we may wind up doing a lot of that anyway, but let's try the software probe first. Okay, so first I'm going to do a memory dump. I'm going to type D for a dump. What we see here is, right off the bat, there's nothing graceful here. It's going to dump the entire 64K starting at address 0. And we'll see if this causes if it hits a tripwire with just the memory reads. Looks like it's continuing nicely, so at least down here there's nothing that we hit. So this gives us the 16 bytes per line, first in hex, gives us the address and then the data, and then it gives us the ASCII value of that if it's printable. So it looks like we're up here, well, we're still in the EPROM itself. So first we saw my code go by, and now we're just up in the EPROM. This is all Fs. So I'm going to watch this for a while. I think we left this at 2400 baud, but it's still going to take a while for this thing to dump. So I'll come back after it has finished dumping and we'll scroll back and see what we found. All right, so this finished dumping, we can see here it goes all the way up to FFFF. And, that seems quite remarkable that this finished dumping, we didn't hit any tripwires. It was successful in its dump. As I scroll backwards here, we can see, okay, this is where we started. This is my sign on. This is just our code, my code that's running this probe program. Then we get up all of these F's. This is just the unprogrammed portion of the EPROM. Now this looks different, obviously. This looks more like RAM. RAM when it first powers up favors some typical pattern, and this is a repeating pattern. There's some F's, DF's, every other one's a 0, it looks like. So to me, this looks like completely uninitiated RAM. Then we go up a little further. What do we see? Still more RAM. Okay, now we get up 4000, and what we're seeing here is completely different. This goes from just values, favorite values in the RAM. This is what we typically see if it's just completely unmapped space, where basically the data byte that we get back is the low address that was just put on the bus. And this is common for a memory dump to give you back the low address byte, since that's what the last thing that was put onto the bus right before the read. And after the processor puts the low address onto the bus, it tri-states the bus. And with nothing else driving the data bus, those bits will remain until they eventually bleed off. So if we just we put the address out on the address data, and then we switch over and read the data in, more often than not, we just get the value back, the low byte of the address back that we put out. So that tells me that all of this is completely unmapped. There's nothing out there. We're just reading our values, our addresses back. And so that goes on up. There's 500. Now we're into the 6. Now what's a little bit disappointing is that I saw this block of RAM that is the 8K Toshiba device. That was up here from 2000 to 3FFF, but I didn't see anything up here that looked like the 8155 RAM. So there should be another 256 bytes up here in the 8155, and I didn't see that. So I'm a bit worried that that's not there. Don't get me wrong. I'm tickled about what we're seeing here, and that this dump completed. So that means that there were no tripwires. This is what's important. There's no tripwires on a memory read. So we can read memory at will, and we're not reconfiguring. We didn't go into a hibernate state. We didn't go into a halt. We didn't remap the memory. So there was no problems in doing a read, and that's very good news. Let's see if we can do a write. What I'm going to do now is I'm going to do a fill, reset, space, fill, and then capital this time, AA. Oh, okay. Yeah, I think what happened was I had lowercase before, but at any rate, we got the fill to work. That's good news. I'm going to go ahead and do another dump. We'll see what this looks like. And so we're just going to do a dump, let that go, see what that looks like, and see if we can now see where we filled the RAM with that AA. All right, so I'll come back when this is done. Okay, we're back. This dump finished quite a while ago. It just took me a while to get back to this project. So let's scroll back to the top of this dump and take a look at what it looks like. Remember, we filled this memory with AA. All right, there's our code that's in the EPROM. Of course, it just started at 0, goes on up, and it tried to fill each of these memory locations with AA. So that EPROM should go up to 2000. And at 2000, that's where it looked like it changed over. Yep, here we go. So at 2000, this is where it started finding RAM, and it wrote that AA into the RAM, and so that's still there. And so that's 8K RAM, and if it's contiguous, it should go up to 3FFF. And there we see it, 3FFF. That's the end of that RAM. Now, I'm a bit disappointed. I was hoping to see the 8155 EPROM take off there, but it didn't. And You know, I don't see, if I look through this, this is all just unclaimed memory. It's not mapped at all. We're just getting back the data that's the address like we did before. So just quickly, I don't see that we're seeing that 8155. This goes all the way up to FFFF. I didn't see another block of RAM. So in the next test, what we're going to do is just do a memory map. So I'm going to give it the memory map command. And it said that it found the block from 2000 to 3FFF. And that's that block we already found. That's that Toshiba 5565. So that 8K, it found that, but it only found that one block of RAM. And do it again, and the answer is not any different. You know, I have kind of mixed emotions on that. I'm very happy that, you know, I'm thrilled the program completed, because that tells us, you know, that's another test that we've written to the RAM, we've read from the RAM, and we've written and read from the EPROM. We've written this whole memory block. And in doing all of that, writing and reading this memory block, we didn't hit any tripwires. So we didn't put the board into hibernate, we didn't put the board into a halt, we didn't change a memory map, we didn't do anything. And, you know, that's all good news. But we also, it didn't find the 8155. So either it's hiding where my program couldn't find it, or it isn't decoded and mapped. So don't get me wrong, I'm thrilled for what was successful. You know, that little RAM, this you know, little serial board, it did its job. It went through, it helped us find the RAM. We tested it a couple of different ways. And so now we'll be able to start writing code using this RAM on board. So now we can go back to having a stack and actually writing real code and not having to fight this thing. But it is a little bit disappointed with Onset, I guess, if that truly isn't mapped. This 8155 isn't mapped. Now, I guess I need to come in and check this 8155, maybe swap it out with another one, and see if maybe there's not a problem with that chip. But right now, it doesn't look like that 8155 memory is mapped. And obviously, the I/O on that should be port mapped. Okay, so I'll figure that RAM out later. Another thing I found is, I was just here before I got back on, I was playing with this dump, and I found that if I adjust the voltage, I can get this thing to reset, or at least start getting junk. I can get it to lock up. So I think what's happening is, you know, none of this stuff over here is CMOS, and certainly this isn't a CMOS EPROM. I think what I need to do is, I think I might need to swap this out for a CMOS EPROM. I might need to change some of these to CMOS, because I think I'm overtaxing this converter now. You know, there isn't that much bulk capacitance on this board. So I think this thing switches on, it charges up, switches off, and this is taking so much current that the voltage is collapsing. I'll have to put it on the oscilloscope here and actually look at that. But I'm not too worried about that yet, because if I get the voltage band just right, it all seems to work okay. Now, some more big news in the documentation. A viewer sent me a link. They left a comment. The comment had this link to this document from Iceland, and this is some kind of a remote sensing device. And for some reason, he then deleted that comment. But fortunately, YouTube had emailed me the comment with a link in it, so I was able to get the document. Because, and I don't know why he deleted it, but if you're the viewer that sent this document, you know, I am really thankful for this document. This is some great stuff. What this has in it is, it's got a number of manuals, so not just cut sheets or data sheets, but actually manuals for some Onset cards. It had some memory cards, a UART card. Let's see, I think there was also some analog to digital and digital analog converters. So anyway, a number of Onset cards, and one of those is the CPU-801. Now the CPU-801, that's a Z80, a National Semiconductor Z80 kind of clone. But this has got a lot of description of this card, how it's memory mapped, and going into the wait states, coming out, or going into the hibernate, coming out of the hibernate. And it's got timing diagrams, descriptions, but it's also got a schematic. Now, you know, when somebody comes up with a design they like, they just reuse that design. So I would not be surprised at all if this little buck converter on this schematic is pretty much the same as what I have on this board, this 8085 board. So it'll be good to compare it to this, but you know, I can kind of use this as a starting point when I'm looking at this, or if I wind up having to draw my own schematic, you know, I can compare it back to this. The other thing is this has got some of the chips that we were wondering about. You know, here's a 4040, that's a counter. We were wondering in the last video, what in the world is that 4040 doing? Is it dividing the clock, or is it slowing things down, or is it, you know, part of the sleep state or low power state? Actually, what they're doing with this 4040 is when this comes out of a hibernate, the 4040 gives us, you know, this is off of output 12. So it gives us, you know, like 2 to the 12th ticks before it allows the processor to start fetching instructions. So that allows the oscillator circuit to come up and stabilize before it kicks the processor back into place. So it looks like that's what's happening with this 4040, and I've got the 4040 on this board also. So that makes quite a bit of sense with that. So that may answer that question. A lot of these chips are just the same. I've got the 7474, 74139, so we can see how this is set up. Now, there's a lot of differences in this. This doesn't have any RAM on this board. It has a real-time clock. It does have the 2764, and it does have a national I/O, or there's a note down here, but also using the 8155 I/O, and they've got addresses down here. Now, an interesting thing, if we look at this, it says the 8155 has the RAM and the port mapped out, so they're FC and FD, and the programmable parallel I/O is at FC and FD also. Here they say that if you go into a wait, you write to location FA00, and to go into a stop, you write to location F8. So F8 to stop, FA to go into a wait. Now this is exactly what I was worried about would happen with this board. You know, we knew we had to go into a wait, and we knew we had to go into a hibernate. We just didn't know how. On this other one that we've got the schematic for, this is how we do it. We write to these locations, but we just wrote to every memory location, and we did not put this into hibernate. So that's one thing it's doing differently on this board. And, you know, maybe it's starting to look like the hibernate, the latch, and so forth are done with an onboard port rather than just memory mapped. Now there's one more thing, and I guess I'm kind of glad I didn't know this when I started looking at this board, and that is they have an alternate memory map. The way that works is this has this 2764, and they've got a latch over here, this 7474. When this first comes up from a reset, the 2764 responds to every address. So it's just mapped over and over and over again. It's overlaid at every address. It's re-overlaid. So no matter what address you pick on the upper address bits, you will get this 2764. Then what happens is, as soon as you read its native address, which is E0 to F7FF, as soon as you read anywhere in that range, its actual natural address, then the mapping changes, and so this EPROM is only available at that address, and then everything else comes back into play. The real-time clock, the 8155, or this NSC 810, everything else comes back into play. So it does a remap of all the memory. And I don't understand that, because that puts the 2764 at the very top of memory. And the problem is that since this is at the top of memory, you can't use any of your interrupts. All your interrupts are gone, because your interrupts, I guess what you would have to do is you would have to write your interrupts into the RAM, which are now at 0. Well, no, wait, this has a real-time clock. You know, this doesn't have any RAM on it. I'm not sure what. They're expecting you to use another card that has the RAM and EPROM. But I guess the upshot of going over all that is that This is kind of what I was worried about, remapping the memory or tripping the memory. But fortunately, we just did writes and reads on this board, and we didn't do any of that. So I think this 8085 version is a much superior design than this CPU-801 version. I'm not sure what they were going for. One of the only things that this has got going for it is it's got a real-time clock, where this doesn't appear to have a real-time clock on this 8085 version. So to the person that sent me this document, and this is a bigger document. This is only that one section on this board. This had 140 pages of manuals for the various components inside this data acquisition, this remote sensing system. This is from '89. So I appreciate the people making this document, including all of the manuals in it, and then I really appreciate the person that yesterday or today or just recently posted that comment, even if they did delete it. But feel free to put that comment back out. I will put a link to this document as well as all of these documents back in the description or in the pinned comment on this video. Okay, so I'm really happy with this. We have read the board. We walked up to this. We didn't know anything about this board when we started. Plugged in the serial dongle, ran this ramless code, found where the RAM is, at least that block of it. We've still got all of these jumpers. We don't know how to configure this board. If I can figure out these jumpers, maybe we can bring that 8155 back in. Maybe that is actually mapped somehow. But if we can find the documentation, that would be, just absolutely glorious. If we could find the user's manual, the equivalent, this user's manual for the CPU 8085. Okay, I will put this on the shelf for the time being. I'm going to get back to my Intellect system and some other projects I got going on. But wanted to give you a catch up on this. If this board actually runs, put out another call for documentation, let you know the status. Just see if anybody else has any ideas on this board. And again, if you come across one of these things, it'd be a fun thing to pick up. And if you find any other C44 cards that you don't want, let me know, because I may be interested in getting them. Okay, that's it for this video. I appreciate you watching, and I will talk with you later. Bye-bye.